A coal power plant is one of the most iconic images of industrial civilization. Most people recognize them instantly. Massive chimneys rising into the sky, hyperbolic cooling towers releasing white plumes, gray buildings surrounded by mountains of black coal. For more than a century, coal power plants were the backbone of electricity generation, powering cities, factories, and homes. They symbolize both progress and pollution at the same time, the energy that drove development and the emissions that now threaten the climate. To understand why coal plants dominated for so long, and why the world is now moving away from them, we need to explore in detail how they actually work. Everything begins with coal itself. Coal is not just a rock, but fossilized biomass, the remains of ancient plants that lived hundreds of millions of years ago. During the Carboniferous and Permian periods, Earth was covered by vast, swampy forests. Plants died, fell into waterlogged ground, were buried under sediments and cut off from oxygen. Over millions of years, pressure and heat transformed them first into peat, then into lignite, and eventually into bituminous or anthracite coal. Every piece of coal is a capsule of ancient solar energy stored in the carbon bonds of prehistoric vegetation. Today, coal is mined either in deep underground mines or in huge surface operations where entire landscapes are stripped away to reach coal seams. Once mined, coal is transported to power plants by trains with hundreds of wagons, by trucks, or by ships across oceans. A large coal power plant can burn tens of thousands of tons of coal every day. That is why coal yards around power plants look like black mountains, massive reserves ensuring the plant does not stop if deliveries are delayed. Once coal arrives at the power station, the first step is preparation. Big lumps of coal would burn inefficiently, so they are crushed and ground into a fine powder. Pulverized coal has a huge surface area and burns much more quickly and completely. The powder is mixed with air and blown into the furnace. At the heart of the plant is the boiler. This is not a simple household boiler, but a steel structure as tall as a building, lined with tubes carrying water. Inside the furnace, pulverized coal burns at temperatures above 1,200 degrees Celsius. The heat turns water in the tubes into steam. Not ordinary steam, but superheated steam at over 500 degrees Celsius and hundreds of bars of pressure. This superheated steam has enormous energy and is ready to drive turbines. The steam flows into the turbine, a gigantic rotor with multiple stages of blades. The steam expands, hits the blades, and spins the turbine at thousands of revolutions per minute. The turbine shaft is connected to a generator, a massive cylinder where coils of wire rotate inside a magnetic field. By electromagnetic induction, mechanical energy is transformed into electrical energy. This is the crucial conversion. Chemical energy in coal becomes thermal energy in combustion, kinetic energy in steam, mechanical energy in the turbine, and finally electricity in the generator. The steam leaving the turbine has lost much of its temperature and pressure. It must be condensed back into water so it can be reused. This happens in the condenser, a giant heat exchanger where steam passes over tubes cooled by water drawn from a river, lake, sea, or cooling tower. The steam condenses back into liquid water and is pumped back into the boiler to repeat the cycle. This closed-loop process is known as the Rankine cycle and is the foundation of most thermal power plants, whether coal, nuclear, or gas. Cooling is a critical part of the process. That is why most coal power plants have iconic cooling towers. The white plumes rising from them are not smoke but water vapor. Smoke and exhaust gases come from separate tall chimneys. And it is those exhaust gases that are the Achilles heel of coal plants. Burning coal releases enormous amounts of carbon dioxide, the main greenhouse gas driving climate change. It also produces sulfur dioxide, which causes acid rain, nitrogen oxides that contribute to smog, particulate matter, and toxic heavy metals like mercury and arsenic. Modern plants are equipped with complex cleaning systems. Electrostatic precipitators capture dust, flue gas desulfurization units use limestone to neutralize sulfur dioxide, and catalytic converters reduce nitrogen oxides. But carbon dioxide remains largely unchecked. The solid waste of combustion is ash and slag. Some fly ash can be reused in cement or concrete, but most ends up in landfills or ash ponds, sometimes contaminating soil and water. A single large coal plant can generate millions of tons of CO2 and hundreds of thousands of tons of solid waste each year. Efficiency is another challenge. Traditional coal plants convert only about 33–38% of the energy in coal into electricity. The rest is lost as waste heat. The most advanced supercritical and ultra-supercritical plants, where steam reaches extreme temperatures and pressures, can push efficiency above 45%. Combined heat and power plants or cogeneration facilities can improve overall efficiency by also supplying district heating to nearby cities, reaching up to 70% utilization of the fuel's energy. Running a coal power plant is an intricate dance of machinery and human control. Conveyor belts feed coal continuously. Mills grind it into powder. Fans inject the right amount of air. Pumps push thousands of liters of water per minute through boiler tubes. Turbines spin at dizzying speeds, and generators produce hundreds of megawatts. In the control room, operators watch over hundreds of gauges and screens, constantly adjusting parameters. Any imbalance, too little air, too much fuel, a pressure fluctuation, can cause efficiency losses or even accidents. Historically, coal power plants built the modern world. In the 19th century, the first steam engines ran on coal. Trains, factories, and the earliest electric grids all depended on it. In the 20th century, coal became the backbone of industrial nations, providing cheap, stable power. Without coal, there would have been no mass urbanization, no industrial expansion, no modern consumer society. But coal has always had a dark side. Smog-choked cities, acid rain damaged forests, miners suffered lung diseases, and eventually scientists realized that CO2 from coal plants was destabilizing Earth's climate. By the late 20th and early 21st centuries, coal had become the symbol of dirty energy. Many countries now shut down old coal plants and replace them with renewables, natural gas, or nuclear. Yet in other regions, coal still dominates. China and India continue to build new coal stations to meet surging demand. Countries like Poland or South Africa remain economically and politically tied to coal. The future of coal is uncertain. Some hope for carbon capture and storage (CCS) technologies that would trap CO2 and bury it underground. In theory, this could make coal clean. In practice, CCS is expensive, energy-intensive, and not widely deployed. Others argue the only solution is a complete transition away from coal. So how does a coal power plant really work? In simple terms, coal is burned, heat makes steam, steam drives a turbine, the turbine turns a generator, and electricity is produced. But in reality, it is a vast orchestra of machines and people, transforming ancient fossilized forests into the energy that powers modern life. It is both an engineering marvel and an environmental dilemma, a reminder of human ingenuity and of the costs of our progress.